Hi, everyone. We are very happy today to have Flavio Calmon speak in our seminar. Flavio is an assistant professor of electrical engineering at Harvard. Before joining Harvard, he was a data science for social good postdoc at IBM Research in New York. He received his PhD in electrical engineering and computer science at MIT, and his research develops information theoretic tools for responsible and reliable machine learning. And today he will tell us about facets for machine learning. All yours, Bobby.
Great, thanks. So thanks for joining. Today I'm going to talk about some of the recent work that my group has been doing on facets of fair machine learning. I'll explain it a little bit exactly what that means. The work that you're going to hear about today was done by a wonderful group of students and postdocs at Harvard, Shahab and Hewan, who were at Harvard, and now they've moved on to faculty life. Hao and Sean, who Sean just graduated, and they're also moving on to industry. Luke as well, Winston, Lucy, Carol, and Felipe. Lucy and Winston were undergrads here at the college when they were working on this. So this is the agenda for today. I'm going to start with a very brief introduction to information theory, just to help you understand what is the perspective that I'm coming from. Then I'm going to talk about some of the limits of group fairness and fairness interventions. Then talk about another problem that we've been thinking a bit about called predictive multiplicity and the Rashomon effect. And if I have time, I'm going to conclude with some of the ongoing research challenges that we've been looking at. So to just start off with a little bit about information theory and the information theoretic perspective, I would love if someone would be brave enough to unmute themselves and try to answer this question. What is information? Or maybe post it on the chat if you're feeling that you don't want to have your answer recorded. So students who have taken a class with me know that I love awkward silences. Like that's like what energizes me for the rest of the talk. So
there's a response in the chat.
Oh,
knowledge that can be used.
Yeah, knowledge that can be used. That's a good way of framing it. Not some data that you can process, that you can learn something about it. From an information theory perspective, when I think about information, I think about it as the resolution of uncertainty, right? So information is some quantity that you observe or measure or receive, and that helps you resolve some uncertainty. So if I tell you that the sun will rise tomorrow, that is a less informative statement than if I go here on my table and roll 2 dice and say that the sum of the faces of the dice roll of the true dice roll is 12. Right, and the reason for that is because the sun will rise tomorrow we know that it will rise with probability very close to 1, but if I look at the outcome of a dice roll, there's significantly more uncertainty. So in information theory, when we think about information, the way we usually model it is by using probability distributions and random variables and their distributions. And we, by analyzing properties of these distributions, we try to conclude something about a system or the limits of a system that processes, transmits, compresses, represents, or learns from data. So information is a resolution of uncertainty. And what is information theory? Well, information theory, if you look at the Information Theory Society website, you will see a definition like this. Information theory encompasses the processing, transmission, storage, and use of information and the foundations of the communication process. In the building that I'm standing here now, the SEC building at Harvard, probably most of the people here would see their research somehow reflected on this statement. But what makes information theory unique is that we can use it to mathematically characterize the fundamental limits of information systems, of systems that transmit data, of systems that represent data, and systems that learn from data. And the way that this is usually done in problems in communications and problems in compression and problems in learning is usually via something that I like to call the information theoretic blueprint, where you start with a problem, and then you model this problem, usually abstracting away computational considerations and focusing on the underlying information as modeled by probability measures. and then perform some mathematical analysis on this using probability theory, statistics optimization, functional analysis, and so on. And success is achieved when by analyzing these models, we can identify operational limits of information systems, new algorithm coding techniques, and so on. So today I will be applying this blueprint for some problems in responsible and fair machine learning that I will be presenting in a little bit. But I just want to mention that, especially for the students who are on the call, that information theory is connected to many other fields like probability theory, statistics, mathematics, economics, computer science, physics, and communications theory. And what my research group does at Harvard, what we try to do, is to add another petal to this flower and to use information theory to understand certain limits of learning, specifically when it comes to privacy, generalization, fairness, and so on. And this application of information theory to machine learning is a natural evolution of the field. Information theory is a really interesting field because it actually has a birth date. So you can claim that information theory was founded with the publication of Shannon's paper, A Mathematical Theory of Communications in 1948. And that paper established fundamental limits of communication systems and compression and so on. And for the next decades, engineers and computer scientists and others have been building reliable data communication systems that process and store information, and have been trying to achieve these limits. And the wide deployment of these systems have led to the fast development of machine learning, because now we have a lot of data and fairly cheap computing power widely available. And the question that I ask in my research is that, given the new challenges exposed by the fast development of machine learning, can we apply information theory to address these challenges? And specifically, challenges that emerge when you're using machine learning algorithms and automated decision-making and applications of individual level consequence. So I know I'm preaching to the choir here, but just to make this point that data-driven algorithms are increasingly used to support decision-making and applications of individual level consequence. So these applications include, for example, automated grading. One example of this was when the UK government used an algorithm to assign grades to students in the UK in lieu of in-person A-level exams that couldn't be held because of COVID. And there were many reports showing that these algorithms were biased. This trend continues around the world, particularly in places that I'm really interested in, like in Latin America. This is a piece of news that probably you are not familiar with, but this came out about a year ago when the Ministry of Education in Brazil announced that they would use AI for automated grading of the National University entrance exam. This is an entrance exam that every single Brazilian student has to take to enter the university. I took this exam when I was applying to universities in Brazil. And the goal here is to use AI, or basically automated algorithms, to assign grades to the handwritten essay components of the exam. And these algorithms are being deployed in many other places. Another example of this is also an article that came out at the Wired magazine last year, where Microsoft AI was deployed in the province where there was a partnership between Microsoft and the government of the province of Salta in Argentina, where they were using algorithms to predict things about students, including dropout, and it was used to predict teenage pregnancy. So these are examples where probably algorithms shouldn't even be used. Machine learning methods are being deployed by governments across the world, and particularly Latin America. That's a place where I'm really interested in terms of applications. This is at risk of creating, for example, algorithmic leviathans. These are algorithms that control access to critical opportunities to large swaths of the society. For example, if I'm a Brazilian student and I'm taking the university entrance exam, I may not have the option of not having this algorithm applied to my data. So we want to make sure that these algorithms are deployed responsibly. Challenges, contexts, and regulations change in many different places. And what I'm going to talk about today is some theoretical results related to the development of responsible machine learning algorithms. And I just want to mention that theory is a small part of this puzzle. Like, this is a very complicated problem that has to take into account many different perspectives that go from ethics to law, to computer science, engineering, mathematics, and so on. Theory is definitely not the solution, the solution for the problem, but I think it is a very important facet because it tells us some of the fundamental trade-offs when you're designing these systems. And today, what I'm going to do is that I'm going to give a brief overview of two facets of this problem. This is just an illustration that was generated by DALL-E with the prompt of a photorealistic multifaceted polyhedron against a white background. And it's a surprisingly good illustration, which says a lot about the evolution of these algorithms. And I wanted to show this here just to illustrate that, again, this problem of fairness and responsible development of machine learning algorithms is a multifaceted problem. And today I'm going to talk about a few of these facets that we've been working on. I'm going to talk about group fairness and predictive multiplicity. There's another thread that we've been working on as well, known as fair use. I won't have time to talk about that today. But the work that I'm going to be presenting here is based on a sequence of recent papers published at the latest NeurIPS and FACT on these topics. So if you want to learn more about them, you can check out our papers. So to start off, I'm going to start with group fairness and talk a little bit about fairness interventions and also the limits of ensuring group fairness in in the deployment of machine learning. And I'm going to define exactly what I mean by that. So consider the following problem, where we have a data set, and from a data set, we can produce a sample X, and this sample is fed to a classifier that's going to output a score or a probability distribution over classes or a decision H of X. And what we're trying to address here is the following challenge, is the challenge of group fairness, where the performance of the classifier may change across different population groups. And we do not want that performance to change significantly across groups. What do I mean by performance? Here, I'm going to leave the performance metric purposefully vague. I'm going to define it, the metrics we look at a little bit later. But what I mean by that are things like accuracy, differences in false positive rates and false negative rates. And what do I mean by population groups, right? How are these groups defined? Well, this is a tricky, tricky issue, right? One way of defining different population groups, if you look at the recent the recent blueprint for an AI Bill of Rights launched by the White House Office of Science and Technology, is that you can define these groups, for example, in terms of race, color, ethnicity, sex, religion, age, and so on, or intersection of these attributes. So just to say a little bit more about defining these groups, fairness interventions that require pre-specified population groups during model development may miss vulnerable populations identified post-deployment. And population groups may intersect in terms of combinations of personal attributes, like the ones that I mentioned earlier. There are very interesting definitions developed by folks that are on this call in terms of multi-accuracy and multi-calibration that aim to ensure comparable model performance across computationally identifiable groups in a data set. Though I'm not going to take such a general perspective of defining these groups, because I'll be looking at a more I don't want to say standard, but another way where you have a certain number of groups in the data set and you want to ensure equalized performance in terms of these pre-specified groups. But what I'm eventually going to present is a post-processing method that is very flexible, because you can change or correct the predictions of a classifier to groups identified only post-deployment. If you have a pre-processing method, for example, which you're trying to ensure fairness based on that, you have to know a priori which is the groups for which you want to equalize the performance of your model. And talking about post-processing and fairness interventions, there are many fairness interventions that have been proposed out there. Roughly speaking, these methods can be divided in three categories: pre-processing methods, where you change the data prior to training a model; an in-processing method, where perhaps you add a penalty to the model or you retrain the model several times in order to ensure a given fairness constraint; and post-processing methods, like I mentioned, where you train the model as you usually would, and afterwards you try to change its outputs in order to ensure a given notion of fairness. And in its simplest form, and this is a way of defining group fairness that is very common in the literature, is that you can build these group fairness metrics in the following way. In the simplest case, where you have binary classification, where a classifier output is either a 0 or a 1, and given an input example X in your data set, your classifier output denoted here by y hat for each H of X, and a given set of group attributes that I'm going to denote by this variable S, one common way of building group fairness metrics is in the binary case is the following, where you build a confusion matrix, say for one population, and a confusion matrix for the other population. And by comparing the entries of these matrices, you define different fairness metrics. So for example, if I'm try to impose that the average number of outcomes marked as 1 across different populations is similar, this is known as statistical parity. You can try to equalize false positive and true positive rates. This is known as equalized odds. But as many of you know, there are combinatorially many other metrics and trade-offs that you can derive from this table. What I'm going to be talking about today are, and the metrics that we're going to be using are group metrics defined for probabilistic classifiers. What do I mean by that? We're going to be assuming that the output of your classifier is a score. What that means is that the output of the classifier is a probability distribution over classes. So you can think about that as, for example, a neural network with a softmax output layer, or for example, logistic regression. Instead of getting a 0-1 output, you get some score between 0 and 1 instead of being strictly 0 and 1. And in this case, the fairness criteria that we mentioned earlier, like statistical parity and equalized odds, can also be generalized to this setting. And these are just, I'm just going to present the definition here, but these are natural generalizations of statistical parity, equalized odds, or equalizing the accuracy of the model across these pre-specified number of groups S. The reason we're going to do that for a very important reason, and I'm going to show this in a yellow box because I want y'all to remember about this later, is that several score-based group fairness metrics can be written as linear constraints on the classifier. So when we cast these metrics in terms of the output score of a model, basically a probability distribution over classes read from the output of your model, these fairness metrics, they become linear constraints. Whereas if you're working with the thresholded scores, these are non-convex constraints that are very hard to deal with. And just to continue setting the stage here, when you talk about these group fairness metrics like equalized odds and statistical parity, the way fairness interventions are usually compared is in the following way. And this is a figure borrowed from work done by Sorel Friedler's group a few years back. But this is representative of how these methods are often compared, where you select different data sets, things like adult data set, German data set, the Compass data set. Many of these data sets are overused. And you produce the following graphs, where on the x-axis, you have some measure of group fairness. For example, equalized odds. Here, CV represents something that is similar to statistical parity. On the y-axis, you have the overall accuracy achieved by the method. And then you plot different methods in terms of their achievable fairness accuracy frontier. And there are many group fairness interventions out there that one can compare. This is a recent survey produced by Hart et al., where they identify 341 publications with different fairness interventions that try to ensure some form of group fairness. So there are really many, many methods out there. And what I'm going to talk about next is that I'm going to propose yet another group fairness intervention. So we're going to increase this number to 342, or maybe some other number. But this is an interesting method because I think it overcomes certain limitations that exist in methods that are out there. It's based on information theory ideas. And later on in the talk, I'm going to give a converse result showing that the method that we're going to show, as well as some others that exist in the literature, are very close to the information theoretic optimal in certain situations. So our goal is to design a group fairness intervention, and we want to design group fairness interventions that we can apply to very large data sets with millions of samples, and in order we can fine-tune models using very large data sets, and that we can ensure notions of group fairness for in multi-class classification problems. And also we can ensure fairness for multiple potentially intersectional groups. And there are many fairness interventions out there, but many of them have certain limitations. They often only consider binary classification, or they ensure fairness for binary groups. Of course, methods that aim to ensure multi-accuracy and multi-calibration circumvent that issue. but there are many other methods that have been proposed out there that consider only two groups. And a lot of the results that you find in the literature, they're only benchmarked on overused data sets, like some of the data sets that I mentioned, ADLO, Compass, and so on, that have fairly modest size. So what I'm going to talk about next is a fairness intervention called fair projection that aims to overcome some of these limitations. They can be fair projection, which I'm going to talk about next. It can be used for any number of classes and protected groups in theory, right? In practice, that depends, that's limited by the number of samples that you have and number of samples of each group. We benchmark it on a data set with over 1 million samples derived from the Brazilian University entrance exam. I'm going to talk about this data set in a little bit. And a key property of fair projection is that it can be applied to any classifier without retraining the classifier. And this algorithm that I'm going to talk about next, it's based on an optimization formulation called information projection. An information projection is an optimization problem that appears in information theory and other areas, and which directly inspires the method that I'm going to talk about next. So let me talk a little bit about information projection and what is that about. So information projection is the following problem. If I give you a measure or a distribution P and a convex set of distributions denoted here by column C, the goal of information projection is to find a distribution within this convex set denoted by this blue ball here that's the closest to P. And usually this notion of closeness is given by KL divergence, where you want to find a distribution in this set C here that it's the closest one to P in terms of KL divergence. So you're minimizing across this distributions in this set and finding the distribution Q that minimizes the KL divergence between Q and P. And usually this set is determined by a finite set of linear constraints, of moment constraints on your distribution. And this optimization appears in many applications in statistics and large deviation theory, universal source compression, and beyond. So you can take this optimization problem and generalize it a little bit, where instead of minimizing the KL divergence between your projected and your original distribution P, you minimize some F divergence between your original distribution Q, your original distribution P and the projected one Q on this set. And if you don't know what an F divergence is, an F divergence is a family of divergences which depends on a convex function F. Examples of F divergences include KL divergence, cross entropy, total variation, Hellinger divergence, chi-square divergence, and so on. So this generalization was introduced by Cheeser in 1995, and you can still generalize this further into a formulation that we called model projection in a paper that we presented a few years back at ISIT. And we changed the problem in the following way. Now, instead of projecting a single distribution P, we're projecting a channel. We're projecting a conditional distribution P of Y given X onto a convex set of conditional distributions. And we assume that the distribution over X, P of X, is fixed. And again, our convex set here is determined by a finite set of moment constraints. And then you have a similar optimization problem where you want to find the distribution Q, another conditional distribution Q that satisfies these constraints, that minimizes the average F divergence. What this means is that this is the F divergence between Q of Y given X and P of Y given X averaged over your fixed distribution X, which is fixed. And this formulation is not quite a direct extension of information projection applied to the joint distribution, because X might be defined over an infinite data set, and you have to take a little bit of technical care to show that this is a well-defined optimization problem with a unique solution. So given this formulation, this optimization problem, model projection, we use this to build a fair projection. And here, it's our conditional distribution P of Y given X will be a classifier. And again, because here we're seeing your classifier as a channel, as a conditional distribution that takes it as an input a sample X and outputs a distribution over classes, right? So if you think about a neural network with a softmax output layer, the input for that model is a sample X, and the output is a probability distribution over C classes. And just like in model projection, we projected a conditional distribution onto the set. Here, we view our classifier as a conditional distribution, and we project it onto a given convex set, where this set is the set of group fair classifiers. And here, what I mentioned earlier comes into play. I mentioned before that several group fairness constraints, when they're written in terms of the score of the output of a classifier, they can be written as linear constraints, right? So we can define this abstract set here in terms of the set of all classifiers that satisfy a given fairness constraint. And then the problem of producing a fair classifier, given a classifier that doesn't satisfy these fairness constraints, can be cast in terms of a model projection problem, which we call fair projection, because we're choosing these constraints to be our fairness constraints, where we map our base classifier onto the set F in order to minimize the average change of classifier outputs subject to these constraints. So a priori, there's no reason to believe that this is a simple optimization problem, or even that we're going to have some kind of closed form or tractable expression for this optimal projected classifier. But it turns out that we have. We can write this projected classifier as a post-processing of the outputs of the original classifier. What does this mean? That you get your original classifier H base, and you multiply its output by a factor that depends on this function phi here. And this function is what we call a tilting, which will depend on the F divergence of choice, how you measure the change in these classifiers' outputs. And it will depend on a set of parameters, lambda, which are dual parameters obtained by solving a strongly convex optimization problems. We call this a tilting function, and finding this optimal tilting function depends on the solution of a relatively low dimensional optimization problem, where the number of parameters in this optimization problem depends on the number of fairness constraints that you have. So what this hints at is that according to this projection formulation, post-processing is optimal. Because the solution of this optimization problem is given by a tilting, by a post-processing of your original classifier. So fair projection is an algorithm that computes exactly this optimal tilting. It is model agnostic in the sense that it's a post-processing approach that can be applied to any classifier post-training. I mean, in order to compute these optimal tilting parameters, you have to solve a convex optimization problem that can be solved using ADMM. So the algorithm is presented here. I'm not going to go into the details. You can look at the paper for the details. But this algorithm takes as input your fairness constraints and your original predictions of your base classifier and a regularization term and your ADMM penalty. But what I want to mention here is that this optimization algorithm is highly parallelizable. So wherever you see an I belonging to N here, these are steps that can be computed in parallel on a GPU. So you can solve it once. These are steps that have to be solved for each point in a data set, and you can just solve it in parallel. And so you can actually implement this optimization problem on a GPU and leverage that parallelization. And we actually have TensorFlow code that does that. And you can prove your usual theoretical guarantees for the performance of this algorithm. You can check the paper for details in terms of its convergence regarding the sample size of the data set that you're using to tune this post-processing, this tilting factor. So let's see how fair projection performs in practice. Here I'm going to present results on 2 data sets, in addition to adult and compass. The reason we show adult and compass because many methods out there, they're benchmarked on these data sets. I want to highlight this first data set here. This is the ENEM data set. It's a data set based on a public access data made available by the Brazilian government on the Exame Nacional do Ensino Médio, the National University Entrance Exam. It has over 1 million samples, and it allows you to really test these methods at scale. And the HSLS data set is a data set also where you predict students' performance in high school. It's also based on open source data made available in the US. So here in these examples, our base model is a random forest classifier. So this is our original model, and on the x-axis we have a group fairness metric, equalized odds. On the y-axis we have accuracy, and plotted here is again these plots where you have the fairness accuracy frontier for different fairness interventions. I want to mention here the reductions approach, which is another fairness intervention that performs very, very competitively. That's designed for binary classification. Here, fair projection can go beyond binary classification, but you can see that fair projection performs really well. But the key advantage here is that the reductions approach, despite performing really well on these benchmarks, it's a method that requires retraining a classifier several times. So it is really slow, especially for very large data sets. And fair projection has runs almost 100 times faster, again, because of this gain in parallelization that we have, and the fact that we do not require retraining a classifier multiple times. We actually searched for several methods out there with code, so we could benchmark fair projection in multi-class classification tasks. Surprisingly, we didn't find many methods out there with available code which we could use and reproduce. We found this one, the mitigating unwanted biases with adversarial learning paper. And here again, we compare it against fair projection in terms of its fairness and accuracy. And you can see that fair projection performs really well. So if you look at these results, especially this result here, what you see is that it's almost like we're having diminishing returns in terms of these fairness accuracy trade-offs for different fairness interventions. So a natural question to ask is, what is the best fairness accuracy frontier? And are these hundreds of existing methods that are out there already close to this frontier? And ideally, the result that we want to find is something that looks like this, where if you give me a given group fairness metric and a performance metric of your model like accuracy, are we close to the best possible trade-off, to the best possible Pareto frontier? Is there a region here that is not achievable? And are we close to an idealized theoretical limit denoted here by a cartoon by this purple line? And this is what I'm going to talk about next. And in order to do that, we're going to have to use some results by David Blackwell, and particularly his result on comparison of experiments, which is a form of the data processing inequality that will allow us to derive this optimal frontier in certain cases. And if you want to see the details of this, you can check out our paper on arXiv on aleatoric and epistemic discrimination in classification. So I'm going to shift gears a little bit and talk about this information theoretic converse result. So again, this is the setting that we're considering, where we have group attributes S, where we have a true outcome Y that's unobserved, right? Maybe you observe this only during training. You're going to, you have your input example X, and this input example X is going to be used as an input to a classifier that's going to produce a prediction Y hat. And what this means is that we have the following Markov relationship, where S and Y goes to X and goes to Y hat, right? In the sense that condition on X, your output Y hat is independent of S and Y, in the sense that it only uses X as an input for its classification. So if you assume that the underlying probability distributions are fixed, so if you assume that the joint distribution between your group attribute S and your true outcome Y is fixed, and that this channel that maps, or this conditional mapping that maps S and Y to X is also fixed, you can think about the set of all possible mappings for a predicted variable Y hat given X. And we denote this by this blue ball here. So when you look at this blue set here, I want you to think about the set of all possible conditional distributions that maps S and Y to Y hat, given this intermediate steps X given S and Y. So this is you can think about this if I were to show, if Y is binary, and if I were to search over all possible binary mappings from X to a binary set, might be randomized mappings. What is the set of achievable joint distributions between Y hat and S and Y? So if you fix a given machine learning model, that gives you a point in this space, right? Because once I fix my model, that gives me a mapping from X to Y hat, and that induces a distribution between Y hat given S and Y. And you can think about, out of the set of all possible row stochastic matrices, all joint distributions between Y hat, S, and Y, the set of mappings that are achievable via mappings from X is a subset of this. So this is the set of all possible conditional distributions given these constraints given by my underlying probability distribution from S and Y to X. So why am I going through this? The reason why this is important is because most fairness and accuracy metrics can be cast, these group fairness metrics can be cast in terms of properties of Y hat, Y, and S, given that your number of groups S is fixed. So you can, if you give me this joint distribution between Y hat, Y, and S, just like earlier I gave you a confusion matrix, right? I can cast fairness metrics and accuracy metrics in terms of this joint distribution. So if we could somehow characterize this orange set, the set of all achievable distributions between Y hat, Y, and S, I could give you the optimal best fairness accuracy frontier for a given fairness metric and a given group fairness metric. So if I could characterize this set of achievable distributions, I could formulate, at least in theory, this optimization problem where I search over this whole set for the mapping that gives me the best accuracy subject to a fairness metric, given that P of Y hat, given Y and S is achievable. And that would give me the information theoretic best. But of course, in order to do that, there are many challenges. The first one is that we need to know the distributions, right? And in practice, distributions are unknown. For the purpose of benchmarking different methods, we can relax that assumption because we can create synthetic distributions or semi-synthetic distributions by resampling from a data set. But the second challenge is that your input features X might be very high dimensional. So even searching over this entire space, solving this optimization problem can be challenging. So the key idea that we use in our paper is that we create a tractable outer bound to this set of achievable conditional distributions in order to achieve an upper bound for the fairness accuracy frontier, a converse, right? So if instead of characterizing this orange set exactly, the set of all achievable distributions given constraints on your data generation process, we can outer bound this set, we can find an outer bound for your fairness accuracy frontier, right? And then we can compare existing methods against this information theoretic best. So just as a warm-up, one way of doing this is using the vanilla data processing inequality based on mutual information. So one way of thinking about this is that given this Markov relationship where you go from S and Y to X and from X to Y hat, we know that the mutual information between S and Y hat is smaller or equal than the mutual information between S and Y and X. So if I can constrain my set here for all distributions between Y hat, S, and Y, whose mutual information is smaller than this value, I found an outer bound for this set. But the challenge here is that this is a single constraint and it might be very loose. It gives us not great approximations for this set. And in order to do this, we need a stronger version of the data processing inequality. And we borrow that from a result from Blackwell on Blackwell's comparison of experiments, where you can, he gives an exact characterization of this set, where you say that this Markov relationship SY, X and Y hat is satisfied if the mapping from S and Y to X is more informative than the mapping from S and Y to Y hat. And the Blackwell's result is stated here, but the way you should think about this is almost like the ultimate form of data processing, in the sense that if you satisfy this condition, then you guarantee that this Markov relationship between X and Y hat holds. And if we could, and this is equivalent to ensuring that for any convex function, phi, the function of this vector P of X and the function of this vector Q of Z, that the expected value under P of X is greater than the expected value of the same function for Q of Z. And so one way of building these upper bounds is to identifying convex sets, convex functions phi, and creating a piecewise approximation of this set of achievable distributions. And we choose piecewise linear functions to approximize the set of this convex set of conditional distributions, which in Blackwell's paper, he also shows it's sufficient. So the key idea here is that we create a piecewise outer bound approximation for the set of these achievable distributions. And you can create this piecewise outer bound if you know the underlying probability distributions by solving a difference of convex functions optimization problem. And this gives us a really tractable bound for the set of achievable distributions, achievable mappings from Y and S to Y hat, which we can solve our optimization problem over. So we can create the set and then measure the best possible fairness accuracy trade-off in terms of this outer bound approximation of this set, and compare that to the performance of existing fairness interventions. So let's do that, and I'm going to give you the results on how this looks. So these are semi-synthetic experiments. So what this means is that we take a data set and we assume that that data set gives us the ground truth. And then we resample with replacement from that data set, and in order to generate more data sets and apply a fairness intervention to the semi-synthetic data set. So in this case, we assume the ground truth and that we know the base optimal classifier. And in this case, we can run this approximation algorithm for approximating the set of achievable mappings and plot what's here in red, what we call the fair front, which is the information theoretic best of what we could achieve, and compare it against the performance of, for example, the reductions approach and fair projection. And as you can see here, we're really close to the optimal frontier. Even though we're getting an outer bound approximation, what these results show is that the reductions approach and the fair projection, at least in these cases, for these data sets and these semi-synthetic experiments, they're really close to the best that we can achieve. So the takeaway here is that we are close to the information theoretic optimal fairness accuracy frontier, and that there is indeed diminishing returns and to continue developing more and more and more fairness interventions in order to improve some fairness accuracy trade-off in order to achieve a better point in this Pareto frontier. So we have further discussions on our paper on the difference between aleatoric and epistemic discrimination. You can see, for example, that a poor choice of baseline model can move you away from that frontier, and that in certain cases, there are certain pairs of fairness and accuracy given a group fairness metric and a predefined number of groups in the data set that you may not be able to achieve. So the takeaways here is that we introduced fair projection, and in binary prediction, fair projection is competitive and runs really fast. And that there really seems to be diminishing returns in designing further fairness interventions, given that we're really close to the optimal frontier. But there's still many problems that we don't know how to deal with. One is, for example, one problem that we've been working on is dealing with missing data. And because that can really, the way you impute missing values on data sets can really impact the performance of a given fairness intervention. So I'm running a little bit behind, so I just want to say a bit on predictive multiplicity and another facet of fairness that we've been working on. And in order to introduce this, I'm going to talk first about the Rashomon effect. So consider again the problem that we've been discussing earlier, where we have a data set X, and we want to train a model H. Here, I'm going to assume that this model is parameterized by theta, for example, a neural network that are weights of the neural network that are going to produce prediction Y. In this case, just as a cartoon example, we're predicting the presence or absence of pneumonia on chest X-rays. So if you were to train a neural network or some complicated model in order to do this prediction task, you're going to probably use something like backpropagation. And there's a bunch of decisions you're going to make when designing, when addressing this problem. You're going to set a random seed in order to initialize your weights. You're going to choose dropout weights where you're going to disconnect your neurons. You might shuffle your batches and determine different batch sizes and so on. We're going to call that some random initialization of your algorithm. So depending on the initialization, depending on these random arbitrary choices made during training, after training, you're going to end up with different models, a model H theta 1, H theta 2, and so on. That even though these models might have very different weights, if you evaluate their performance on test time, they might have similar performance, or basically their test loss might be below a certain value epsilon. This phenomena, where you have multiple different models for a given learning task that achieve comparable performance, is known as the Rashomon effect. This was investigated, for example, by Bryman in 2001, where you have many different models having approximately equal accuracy. And the number of models that you have will depend on this parameter that I'm going to call here the Rashomon parameter that determines the performance level of your model, which is usually limited by the number of samples that you have on a test set to evaluate the model performance. So you can think about the Rashomon effect as partitioning your hypothesis space into sets of good models. And by that, I mean models that achieve loss within a given threshold epsilon. And we call that set the Rashomon set. And the Rashomon effect creates opportunities to improve models without compromising accuracy. And there has been quite a bit of work on this recently. So if we could hypothetically characterize the set of good models, we can search the Rashomon set for models that might satisfy other criteria, like being more interpretable or better calibrated or maybe fairer, without compromising overall accuracy. And this was done in several recent papers, for example, by Semenova, Black, Fisher, Coston, and others. And just to motivate this about the existence of fair models or models that satisfy additional group fairness constraints in our Rashomon set, this is something that we've already seen before, right? So if you look at many state-of-the-art fairness interventions, you see that you can really close the gap, for example, in terms of equalized gods and so on, with very small compromise in your overall accuracy. So the Rashomon effect creates opportunities to search for good models that satisfy additional criteria. But the Rashomon effect also poses different challenges, for example, in terms of predictive multiplicity. So here, predictive multiplicity means that if you give one individual sample, and feed it to these different competing models, even though on average, these models have similar performance, they may produce conflicting predictions for this one individual sample. The existence of conflicting predictions by competing models, this multiplicity of predictions, is what we call predictive multiplicity. And we've observed predictive multiplicity in many classification tasks, including image classification, natural language processing, audio classification, and so on. And you can see these references for other examples. And predictive multiplicity is an important problem because if predictive multiplicity is not accounted for, decisions supported by machine learning models may depend on arbitrary and justified choices made during training. And this is particularly concerning when you have algorithms, like I mentioned earlier, being used as algorithmic leviathans, basically one algorithm controlling access to a critical opportunity for large swaths of the population. Because for one individual, the outcome of that algorithm might depend on some unjustified choice made during training. For example, how I initialized my algorithm. And that's particularly concerning in applications like credit scoring, when you have only few credit bureaus assigning credit scores, or for example, in education. And what I want to talk about next is that I just want to give you some highlights of a recent paper that we had on how we can measure and report with predictive multiplicity. I think there are many problems in this area, like, for example, how do you reconcile conflicting predictors? Should we use a Bayesian approach? Should we ensemble these classifiers? How can we characterize this Rashomon set? I will be talking about one specific problem, which is a problem of measuring and reporting predictive multiplicity, which we discussed in a recent NeurIPS paper. So here's a setting that we consider, where we assume that we have a Rashomon set, and for one individual sample, when we feed it through these competing models, we get conflicting predictions, right? So we might, for example, in this simple case where we're doing classification over 3 classes, one model may say that you have 90% of being class 2, other one might say you have 62% of being part of class 1, and so on. And here this triangle denotes the probability simplex over C classes. So if you give me a set of conflicting predictors, I can collect all these conflicting predictions, or conflicting classifiers. I can collect these conflicting predictions into this set here, which will depend on your Rashomon parameter epsilon, and because that will determine the size of your Rashomon set. So the question that we try to answer is, how should we measure these score variations, right? How should we report and quantify this score variation, particularly when we have multi-class classification? So our goal is to create a function that will map these conflicting scores into the reals that will capture some notion of variance or spread of these scores. And we want this metric, M, that for a given sample will map our conflicting scores onto the reals to satisfy certain properties. We want it to be between 1 and C, where C is the number of classes that you're predicting. So this is predictive multiplicity. So it's the smallest multiplicity is 1, and the highest multiplicity is C, where C is the number of classes that you're predicting. You want your multiplicity to be 1 only if all classifiers in your competing set agree. So every single classifier gives the same prediction. You want it to be C only if all possible corner points of the simplex are achievable, What that means is that I have perfect conflict between all classifiers. I can find C classifiers in my set that predict each one of the classes. And you want it to be monotonic in the sense that if I add more models into my Rashomon set, or I add more conflicting scores for that sample, I want my metric to not decrease, only to increase. So we propose a metric for this, and we call it Rashomon capacity. And the idea is that we model these conflicting scores as rows of a noisy channel. So you can think about that as rows of a conditional distribution matrix. And we compute the capacity of that channel. So we create this metric. This is a way of writing channel capacity. You might be more familiar with the formulation in terms of maximizing mutual information over input distributions. This is the exact same formulation. It's just a more variational form of that, where you were given a set of scores. You find a distribution, probability distribution over competing models. This is what this P of M denotes. It's the distribution over predictions that maximizes this score variation. And this depends on your Rashomon parameter epsilon. And the punchline here is that the multiplicity metric given to the Rashomon capacity, we call it Rashomon capacity because it's the capacity of this abstract channel whose rows depend on your conflicting prediction, that this satisfies the desirable properties that we mentioned earlier. And we can actually compute this in practice using algorithms, standard algorithms that you find in information theory, like the Blahuta-Rimoto algorithm that is used to compute channel capacity. Now, the interesting thing about this formulation is the following, is that for classification in C classes, a direct application of Caruthel-Dory's theorem says that even though you might have a very large number of models in your Rashomon set, potentially uncountable models, for each sample, there's at most C models that capture this score variation as measured by Rashomon capacity. So for each sample, there might be a small set of models whose prediction captures the worst case score conflict. What that means is that if I were to recompute my Rashomon capacity over this smaller number of models, I would get the same value. So I just want to give you some numerical results on a few data sets and how you can actually measure this in practice. So again, these are data sets these are results in 4 data sets, HSLS, Compass, Adult, and CIFAR-10, where we have a training data set and we train a feed-forward neural network on this training data set. And then we get a test or validation data set, and we perform something that we call adversarial weight perturbation, where we perturb the weights of the data of the model by just a little bit in order to not decrease the loss by too much, but to maximize the change in score for a given individual sample. And we add these models to the Rashomon set. Of course, this is not a full characterization of the Rashomon set. This is just an approximation. And then we can compute score variation across this collection of perturbed neural networks. And what's interesting is that across these different data sets, weight perturbation is very effective at finding competing models, much more than retraining and just sampling the Rashomon set by retraining the model several times. What you're seeing here on the x-axis is the Rashomon parameter epsilon, and the y-axis, the measure for Rashomon capacity for those points with the maximum score variation, looking at the tail of the distribution. And you can see that this adversarial weight perturbation can capture quite a bit of score variation across data sets that you wouldn't see by simply retraining. And the other thing that's really intriguing is that we find that many data sets have a high multiplicity tail, that this multiplicity phenomena doesn't impact each sample in the same way. That in many data sets, you have a collection of samples, usually something around 5 to 10%, which are significantly impacted by multiplicity, by this variation in score. And these are not necessarily the points that are near the decision boundary. Often these are points that they could be near a decision boundary, but they can also be outliers in the data. So you can see the paper for more results. And I just want to give you the highlights of a recent paper that was just accepted to FACT on predicted multiplicity and differential privacy, because this phenomena appears in differential privacy training as well. So again, here we have the usual problem that we had before, where we're predicting a sample of label Y given a set of input samples X. And if this is privacy sensitive data, the way you want to ensure this is probably by adding some kind of differentially private method during training, right? So if you want to protect sensitive data, or make sure that an adversary cannot determine if one sample was included or not in the data set. You can ensure this via randomization by, for example, output perturbation. You can ensure DP by changing the weights of your model after training, or you can do objective perturbation. You add the random penalty to your model before, to your loss before training, or doing something like differentially private stochastic gradient descent. But all of these methods, they require some randomness that you add during training in order to ensure differential privacy. So the issue here is that each time the training algorithm is run, because of this randomness that you add, you will end up with a different model. So for example, depending on the seed that you use to choose your random, to seed your random number generator, in order to generate this noise that you're using during training in order to ensure differential privacy, you might end up with different models. And even though these competing models offer the same level of privacy, they can produce conflicting predictions to individual samples. And the key point here is that this arbitrariness cost does not affect all samples equally. So it's not equally distributed across all samples in the data set. So just to give you one illustration on synthetic data, here we're fitting a two-dimensional logistic regression on a mixture of Gaussians, and we retrained 5,000 models and discarding the models with trivial accuracy. Of course, this is not something we would do in practice because it would violate differential privacy, but this is something we're doing here just for illustration's sake. And what we're plotting is the probability of disagreement. What's the probability that a score for a given point will change, given that you retrained for different privacy levels? And for example, you can see here that as you increase your privacy, this point marked in yellow, despite being far away from the border, its score changes by quite a lot given you're in the high levels of privacy. And here the non-private model will give you the decision boundary represented here by the 45-degree line. And we see this in many other applications where this arbitrariness cost due to adding randomness during training in order to ensure privacy, it is not equally distributed across all points, where you have certain points and often certain groups in the data set where this disagreement appears more. Basically, these are samples that have a higher probability of having the output of a model depending mostly on the randomness that you use during training versus actual features used as the input of the model. So the takeaways here is that always measure and report predictive multiplicity. I think that's something that's usually not measured. And multiplicity is a hidden cost of DP, in addition to potentially a decrease in accuracy. We still don't know how to report that cost also in a differentially private way. And decision supported by machine learning models without regard for multiplicity may be arbitrary. The outputs may depend not on evidence that exists in data or some inductive bias, but basically on randomness used during training. And we still don't have efficient methods for characterizing the Rashomon set and reporting multiplicity on a per sample basis. So I'm over time, so I'll wrap up here. So we talked about two problems, group fairness and predictive multiplicity. Another problem that I'm interested in is fair use. So you can ask me about this later. My group has been working on many other projects, including projects on differential privacy. If you want to know what Schrodinger operators and differential privacy have to do with each other, ask me later or look at our paper on Schrodinger mechanisms and calculus mechanisms and differential privacy. And we also have work on generalization, bounds, and more traditional information theoretic work on compression and coding and so on. So again, I'll wrap up here. Thanks for staying a little bit longer. If you found any of this interesting, send me an email and I would be happy to answer any questions that you have.
Thank you very much for the talk, Flavio. We are over time, but if there's any quick question, feel free to ask. Okay, if not, I'm stopping.